Hello everybody, we're going to talk about constructing a function out of nothing. So let's look at a couple of examples of functions first before we do that. So here we have a function, so we're saying this is the function y, so this is y as a function of the variable x because that's the variable that we see over on this side of the equation. We call this the dependent, and it depends on what happens in the other with the other variable. So we call that the independent variable. So this is the dependent variable and the independent variable. And now a couple of other things that we notice about this is there is a coefficient that's attached to this independent variable. This coefficient, this is the rate of change. Okay, and then there's a constant, so we call this constant. It doesn't change with any other variable, so it just stays where it is. This constant term is our initial condition or our starting point. It's the value of y when x is equal to 0, because 0 will always get rid of this rate, right? 0 times anything makes 0, and you're just left with y equals -4. So this is kind of the starting point, the initial condition, and the rate is kind of how it changes with each additional iteration of the x variable or the independent variable. As it grows by 1, the value of y will grow by 2, right? Okay, so those are the things that we put together. So I can graph this. I can make a table of values. Let's just make a graph. So this says y is equal to -4. So that's the value when x is equal to 0, right here. 1, 2, 3, 4. And then the rate is every 1x that we're going to go, it's going to go by 2. So 1x, it's going to go by 2. So this is kind of like the slope of this line. So every 1, it's going up 2. Okay, so that's how I could graph that. Sometimes the order is switched, but you just want to look at what is the coefficient attached to the independent variable. That is the slope. What is a constant term? That is your initial condition or your y-intercept. Okay, so looking at this one, I can tell you right now that the y-intercept is 12.5 and the slope is 7.3. So if I were to graph that, the intercept would be at 12.5, and each time it would grow by 7.3, something like that. This one starts at 200, right? So that's my constant term. This is my rate. So it's going down by 25 because it's negative. So that's this graph. The next graph starts at 200. So some people, like, they want to count individual numbers, but it doesn't really matter. If you scale this down, you say, oh, this is 100, this is 200. And then it's going down by 25 each time. So if this is 100, then it's going to go down 4 times to get, that's 3, well, something like that. So the slope kind of goes down like that. And each time it's going down by 25. For every 1, it goes in the x direction. D, so this one, where's your y-intercept? It starts at 3.2 and it goes down by 9.8 each time. So it starts at 3.2. So it's going to immediately go over the axis and be below about 6, right? Just kind of estimating. This goes down from 3, it goes down about 10, so maybe about 7 or something like that. So the line looks something like this. Okay, so that's how you think about these is you have an initial condition and a rate. And now let's go ahead and build a graph from nothing. So we have a real-world example here of a tree growing, and in day 3 you have a little sprout. Day 4 gets a little taller, 5, 7, a little taller and a little taller. And here's the data that we recorded if we were doing this in a lab or something like that. So what we want to do is, what is the constant rate of change? It looks like for every 1, it goes up by zero point 0.5, and then it goes up 1 again. But now from 7 to 11 would be 0.4, so it actually doesn't go up evenly. So it's not really a linear function that would fit exactly, but I think we can approximate this as a linear function. So let's go ahead and graph it. Graph these points. So day 1, 2, 3, 4, 5, 6, 7. So it's going to start here. And the height is 4.2, so 1, 2, 3, 4, 5, 6. So at day 3, and it might be better if I use a ruler here. Okay. Try to get this as straight as I can. It might be better to use graph paper. Yeah, it's not the best, but it'll work. 3, 4.2, so something like that. 4, 4.7, something like that. 5, 5.1, and 6. Alright, so what we do is we do a line of best fit, and you can kind of just estimate. You want to have as many points above and below the line. So this looks like a good approximation. That's probably a little bit low. I should go a little higher maybe. That's a little better. Okay, so I'm using the top line. So what is my initial condition? So when I build the function from nothing, this looks like it starts about 3, so I'm going to say the height of t for time, that's number of days, is equal to, and then the slope of the line looks like, let's see, so if it goes from up 3 to 6 and over 7, so it's going to be, the slope would be up 3 over 7. So the rate of change in the y versus the rate of change in the x. And any 2 points that you can see where the line crosses, you can use those 2 points and find the slope. So this is t plus the starting initial condition was 3. So that's how you build a function from nothing. And now if you wanted to use this function to find some other value, so now what do you think the height's going to be at day 10, for example? You could just plug that in and say h of t equals 3/7 times 10 plus 3. So 30 divided by 7 plus 3, so I'll use my calculator. So 7.3 will be a good estimate.